Okay. So we're going to start easy and get progressively more interesting. Okay. So in this picture, okay, I've got a really small tree. It's got a root and it's got 2 leaves. Okay. And what we're going to do is you can basically make a decision. You're going to walk from a root to one of the leaves that's coloured grey here. Okay. And you want to do it in the path that's going to cost you the least amount, let's say, of money. Okay, so if I go left here, all right, then I get a cost of 1, and if I go right here, I get a cost of 5. All right, so if I want to minimize the costs, what should I do? Go left, yeah? So you can write this in your notes. Answer, left. Okay? Or go left, even, if you want to have go left. All right? All right. So next. So let's try a slightly more difficult example. Okay? Again, we've got a tree, and I'm trying to walk from the root of this tree to one of the leaves, which are coloured grey again. Okay? And I want to do it in the way that's going to cost me the least. Okay, and now I'm going to note there are actually different ways of trying to solve this problem. Okay, one is I could just check all of the paths from the root to the leaves. Okay, or we could be a little bit clever and realise that that is the problem that I solved in the first part. Okay, if I wrote that as the root, it was left 1 and right 5. Okay? So I know that the cost of being here is what? 1, yeah? 1. The cost of being at this point is 1. Okay, from here to here. Okay? I could also use the same idea for this part of the network, of this tree. Okay? So if I was here, what should I do? Go left or right? Left. And the cost I get from that is 5. Okay? And now notice, I've got a problem that looks like this. I've got a leaf that costs 1, a leaf over here that costs 5, and then a 7 and a 5 and the root. Okay, can you see that that's the same as what I've got out of this? All right? Okay? Oop. Sorry, 0. Yeah. Good. I do check that you're awake. 0. Okay. All right. So I know if I get to this node, I'm going to get the best decision is to get a cost of 1. And if I get over here, the best thing is to go left and get a cost of 5. Okay. So now I'm here. What should I do? Should I go left and get 7 plus 1? Or should I go right and get 0 plus 5? Right. Okay. So it's correct to go this way. So the answer here is cost is 5. Okay. And you notice that we go right, and then from this bit we go left. So right, and then left. Okay? It's not too hard. Okay? So this is basically the main idea of dynamic programming, Markov decision processes, diffusion control, and all the rest of it, okay? One of the key ideas is that we can essentially solve a problem iteratively by starting and inductively solving the problem backwards, okay? Just to really make it concrete, here we go, all right? In fact, yeah, I will do this example, why not? We've probably got the point by this point. But what do you recognize here? We can notice we actually already solved half of the problem in the last part. Okay? So again, it's about this matter of basically solving a problem and storing it and then bringing it forward to the next time period. Okay? So here, we knew the cost was 5. Okay? Similarly, I can apply the same idea working backwards. Okay. Here, I can go right, left, or right, and the cost is what? If I take the lowest cost per choice, 1. Okay. And here, it is what? 0 and go left. Okay. Now let's look at here. I can either go left and get 3 plus 1, or right and get 7 plus 0. So what should I do? Okay, so who says 7? Who says 4 and go left? 4, yeah? And you go left, okay? All right, finally, notice that if I'm now at the root node, and I can go left and get 1, and 1 plus 5, or I can go right and get 1 plus 4, okay? And so, what should I do? Left or right? Right, good, okay? So the answer here is that we get a cost of 5, 1 plus 4, and we go right, then we go left, and then we go right. Okay? All right? So notice it's just the way of breaking down the problem into modular parts and then kind of inductively solving the same problem many times backwards. Okay? Okay? So we can apply this in general. So notice what I did here was I solved this part of the tree, then I solved for this part of the tree, and then I made a decision between the two. Okay, so making a little bit more abstract, okay, we've got something like this. Okay, let's say I've got some big tree, and I've solved it, and the total cost is L left for being here at this node. The cost of all these different choices, the optimal choice is L left. Just like I had here, the optimal choice was 5. Okay? And then there's a cost for moving from the root node to there. Okay? And that's little l left. Okay? Similarly, I've got the same on the other side. The cost for this part of the tree is L right, and I've got a cost for moving to that part of the tree, little l right. Okay? So this isn't even really a question, but notice, okay, notice that if I go left, has a cost, yeah, which is the cost of me moving from there to there plus the cost of being there. All right? So do you believe me that it's L left plus capital L left? Okay? Does everyone agree with that? Yeah? And right has a cost. Well, it's the same thing. It's the cost of moving right plus the cost of being at the place I arrive at. Oops. Told you I make typos. L right. Okay? And then given I've got a choice between left and right, which of the two do I choose? Do I choose the minimum? You choose the smallest of the two. Okay? And the argument, whether left or right, the minimizer is the action or the choice that you make in terms of the movement you make. All right? All right? So the cost of the root node is the minimum, okay, of the two choices that I have. So let A be the choices, and the choices are left and right. Okay. And then I get the minimum of the loss that I achieve from the movement plus the loss that I get from the place I end up at. All right? Okay. Now, in this example, we've covered a lot of the key ideas behind dynamic programming, Markov decision process, and all the other stuff we're going to cover. Okay. This is one example of an equation that's called a sort of a Bellman equation. All right. We'll cover more of these in a minute, but the idea is simple. The loss or reward for being in a certain state, say the root node, is given, the optimal choice is given by the minimum of the sets of choices that I can make at the root node. Okay, where we're looking at the loss being the loss of the loss or the cost from the movement I take plus the cost from ending up in that next state. Okay. Another thing to notice is I didn't need to do this calculation for the root node. Okay, so in the next bit, and you can do this in the comfort of your own home a little bit, is that you should notice, okay, here, convince yourself that the same argument applies for any node, so any circle that I've drawn, in the tree network. That is, that L of x is the minimum, okay, of the cost of the movement plus the cost of the state that I arrive at from that movement. Okay? So just to draw a picture of what I mean here is, let's say I drew some big tree. Okay. And let's say, okay, let's do it like that. I'm really bad at drawing. Okay. Let's say that's node X, and it's not the root, so there's other stuff going on over here. Just imagine this is one part of a massive tree. Okay, so there's more branches and all the rest of it over here. Okay. If I wanted to calculate the cost associated with being at this point X, okay, it would be given by the loss of going left, the node to the left of X, that's the loss of the node to the right of X, okay? Then there'll be a cost for going left from X, and there'll be a cost from X going right, okay? And so the decision that I would make, the loss from being at X, would be the minimum of the action that I take of the loss of X and left plus the loss of the place that I end up with, where XA means, so this belongs to left and that belongs to right. Okay, so exactly the same idea. It didn't matter that calculation that I did, this Bellman equation that I mentioned about when it comes back. So this Bellman equation that I mentioned about, it didn't matter that the calculation was for the root. It could have been anywhere in the network in this tree. Okay, the cost that you incur is the cost of the movement plus the cost of the place that you end up at. All right. Okay. So that's one point to note, this equation that we've been writing down a bit. The second thing to note is that the idea of dynamic programming is the idea that we solve a problem from back to front. So as I say at the bottom here, okay, so essentially iterating on this equation, all right, starting at the leaves and working our way towards the root, okay? So what we're doing is we're breaking a big optimization into lots of little simple optimizations, starting from the leaves and working our way down to the root. Okay? Okay? Is everyone all right with that so far? So two things to take home from this part is one, that we end up with equations that look like this, and two, as we covered over here, essentially the way we go about solving these sorts of problems is we go from the leaves and then work our way down to the root. Okay? Those are the two things to say. All right? So if you understand that, And that made a pretty good start. All right? Okay. Are there any questions at this point? Okay. So now, what I'll do for the next couple of minutes and for the rest of the next class where we have to move somewhere across the street, okay, is I'll start to define for you what this actually means. So not just for this tree example, but for a kind of a sort of set of different types of examples where this method is going to work. Okay? All right. So